அனைவருக்கும் இனிய மாலை வணக்கங்கள். தொன்று நிகழ்ந்தது அனைத்தும் உணர்த்திடு சூழ்களை வாணர்களும் இவள் என்று பிறந்தவள் என்றுணராத இயல்பினலாம் எங்கள் தாய். தமிழ்த்தாயை வணங்கி என்னுடைய உரையை தொடங்குகின்றேன். இன்றைய வெகு சிறப்பாக எங்களது பை கணித மன்றத்தின் சார்பாக கொண்டாடி கொண்டிருக்கின்ற இந்த பை தோராய தினத்திற்காக நிகழ்வில் இணைந்திருக்கின்ற அனைத்து அன்பு உள்ளங்களையும் நெஞ்சார்ந்த வாழ்த்துக்களுடன் வருக வருக என்று நாங்கள் வரவேற்கின்றோம். கற்றது கைமண்ணளவு கல்லாதது உலகளவு என்று சொன்னார்கள். அந்த வகையில் கணிதத்தை உலகெங்கும் கொண்டு செல்லும் நோக்கத்தில் ஒரு நல்ல சிந்தனையோடு எங்களது பை கணித மன்றம் மிகவும் சிறப்பாக தொடங்கப்பட்டு இயங்கிக் கொண்டிருக்கிறது என்பது எல்லோருக்கும் தெரியும். இன்றைய இந்த நிகழ்விலே சிறப்பாக சிறப்பு விருந்தினராக உரையாற்றுவதற்காக எங்களது பை கணித மன்றத்தில் உருவாக்கம் என்றே சொல்லலாம், அரும்பாக்கத்திலே இருக்கின்ற துவாரகதாஸ் கோவரன்தாஸ் வைணவ கல்லூரியிலே பயின்று பை கணித மன்றத்தால் ஈர்க்கப்பட்டு பட்டை தீட்டப்பட்ட வைரம் போல தன்னை புதுப்பித்துக் கொண்டிருக்கின்ற அன்பிற்கும் மரியாதைக்கும் உரிய எங்களது பை கணித மன்றத்தின் உறுப்பினர் டி ஆனந்தன் அவர்கள் சிறப்பாக இங்கே உரையாற்ற இருக்கின்றார்கள். அவர்களையும் நெஞ்சார்ந்த வாழ்த்துக்களோடு வருக வருக என்று நாம் வரவேற்கின்றோம். இன்றைய சிறப்பு விருந்தினரை அறிமுகப்படுத்தி பேசுவதற்காக மலேசியாவிலே பொறியாளராக பணியாற்றிக் கொண்டிருக்கின்ற எங்களது பை கணித மன்றத்தினுடைய அன்பிற்குரிய உறுப்பினர் திரு கல்யாணகுமார் அவர்கள் இந்த நிகழ்விலே வருகை புரிந்து இணைந்திருக்கிறார்கள். அவர்களையும் நெஞ்சார்ந்த வாழ்த்துக்களுடன் வருக வருக என்று நாங்கள் வரவேற்கின்றோம். இன்றைய இந்த சிறந்த நிகழ்விலே நன்றி உரை கூறுவதற்காக எங்களுடைய பை கணித மன்றத்தினுடைய சிறந்த உறுப்பினரும் அறங்காவலரும் ஆகிய விஜயகுமார் அவர்கள் வருகை புரிந்திருக்கிறார்கள். அவர்களையும் வருக வருக என்று நெஞ்சார்ந்த வாழ்த்துக்களுடன் வரவேற்று இன்றைய இந்த நிகழ்வில் கலந்து கொண்டிருக்கின்ற அனைத்து மாணவ செல்வங்களையும் எண்ணற்ற சான்றோர்களையும் மீண்டும் மீண்டும் வருக வருக என்று நாங்கள் வரவேற்கின்றோம். நிகழ்வில் முதலாவதாக இன்றைய சிறப்பு விருந்தினர் அவர்களை, அவர்களுடைய பெருமைகளை, அவர்களுடைய சிறப்பை இங்கே எடுத்து கூறி சிறப்பு விருந்தினர் அறிமுக உரையை ஆற்றுவதற்காக மலேசியாவில் பணியாற்றிக் கொண்டிருக்கின்ற பொறியாளர் திரு கல்யாணகுமார் அவர்களை மேடைக்கு வருமாறு அன்போடு மீண்டும் வாழ்த்துக்களுடன் வரவேற்கின்றோம். நன்றி, வணக்கம்.
Thank you, Chellapalli sir. Good evening, everyone. I welcome you all for this session conducted by PMA, Pi Mathematics Association, to celebrate the occasion of Pi Approximation Day. So, on behalf of Pi Mathematics Association, I take great pleasure in introducing our distinguished speaker, Mr. D. Anand, to the audience. He is currently pursuing PhD in number theory in Madras Institute of Technology, Chromepet, Chennai, and he is also working there as a part-time teaching assistant. He has participated in various competitions, paper presentations, inter-college events, and won several prizes. Some of these events and competitions were also conducted by Pi Mathematics Association. Apart from mathematics, he has great interest in poetic works in Tamil language, and he is taking up his research activities in a very passionate way, and he is very enthusiastic to become a professor very soon. So on behalf of our association, we wish him all the best to achieve his dream as soon as possible. So he has recently joined Pi Mathematics Association, and he is contributing to our activities. So today he is going to start with our first lecture for our association. So, and we expect him to do more kind of sessions and involvement in activities in the future. Apart from this, he has also delivered a lecture. He has also contributed to the popular lecture series of AMT, Association of Mathematics Teachers of India. That is approximately around 4 months before. 4 months before, and the topic was golden ratio and Fibonacci series. So, with this introduction, I hand over the session to Mr. Anand sir to take it forward. Thank you, everyone.
மிக்க நன்றி ஐயா. இனிமையாக, சுருக்கமாக, அழகாக, வெகு தோரணையாக சிறப்பு விருந்தினர் அறிமுக உரையை ஆற்றியிருக்கிறார்கள். அவர்களுக்கு நெஞ்சார்ந்த நன்றியை பை கணித மன்றத்தின் சார்பாக நாங்கள் சமர்ப்பித்துக் கொள்வதோடு, நிகழ்வில் அடுத்தபடியாக சிறப்பு விருந்தினர் டி ஆனந்த் அவர்களை உரையாற்ற வருமாறு அன்போடு அழைக்கின்றோம்.
Thank you, Chellapillai sir, and thank you, Kalyan sir, for introducing me. Okay, I will share my screen now. Is it visible? Vijay Kumar sir, is it visible? Hello, is it visible?
Yes, Anand, it's visible. You can proceed.
Okay, thank you. Okay, good evening, one and all present here. I'm Anand. I'm Glad Pressure, a member of Pi Mathematics Association, and working as a teaching fellow in Mathematics Department of Applied Science and Humanities, Anna University, MIT campus. This is my small contribution to Pi, that I deliver a lecture about history of Pi. These are the contents: introducing, calculating Pi, properties of Pi, facts about Pi, what is Pi, history of Pi, history of calculating Pi, Buffon's needle method, digits of Pi, irrationality of Pi, Pi and the area of circle, Pi in real life. These are the contents I will deliver in the further slides. I will start with introduction. What is Pi? First of all, Pi is nothing but ratio of the circumference of a circle to the diameter. If you take this circle, this is the circumference of the circle, and this blue line is nothing but diameter of the circle. If ratio between these two values is nothing but Pi. What is Pi? By definition, Pi is the ratio of the circumference of a circle to its diameter. Pi is always the same number, no matter which circles you use to compute it. It may be very small, it may be very large. It does not matter. For the sake of usefulness, people often need to approximate Pi. For many purposes, you can use 1.31459, but if you want to a better approximation, you can use a computer to get it. Here, Pi to many more 3.14156 to infinite. It does not have any end. The area of a circle is pi times the square of the length of the radius, or pi r squared. This is pi. History. I will move to the history. Pi is very older number. I think so. Age the pi oda age அப்படினு பார்த்தோம்னா maybe 1000 மேல இருக்கலாம். The Egyptians and the Babylonians knew about the existence of the constant ratio pi, although they did not know its value nearly as well as we do today. They had figured out that it was a little bit bigger than 3. That Babylon's approximation of pi from the fraction number of the mixed fraction number of 3 1/8, and the Egyptians approximation of pi the number 4 into 8 by 9, the whole square. Both the community peoples approximating the pi from 1 decimal place, nearly 1 decimal place. These approximations were slightly less accurate and much harder to work with. The modern symbol of pi was first used in our modern since in 1706 by William Jones, who wrote, "There are various other ways of finding the lengths or areas of the particular curved lines or planes which may very much facilitate the practice. So, for instance, in the circle, the diameter is to the circumference is 1 to 16 by 5 minus 4 by 239 minus 1 by 3, 16 by 5 power 3 minus 4 by 239 power 3 up to dot 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 is equal to is nothing but approximately 3.1459 dot 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 is approximately pi. Pi rather than some other Greek letters like alpha or omega was chosen a letter represent the number 3.149592 dot dot because the letter pi in Greek pronounced like our letter P stands for perimeter. History of calculating pi. This is amazing history of calculating pi. The scientists contributing more about the pi. First, you take Archimedes, the great scientist, great mathematician, Archimedes in the field of 250 BC, the year of 250 BC, and then Newton's and Leibniz, later 17th century. Earlier 18th century, John Macken's formula, and 20th century, Ramanujam, the great legend in mathematics, Ramanujam, 20th century. Until that, electronic computers. Archimedes, 250 BC. The first mathematician to calculate pi with reasonable accuracy was Archimedes, around 250 BC, using the formula A equal to pi r square. Using the area of a circle, he approximates pi by considering regular polygons with many sides inscribed in and circumference around a circle. Since the area of the circle is between the area of the inscribed and circumscribed polygons, you can use the area of the polygons, which can be computed just using the Pythagoras theorem to get upper and the lower bounds of the area of the circle. Here you just take circle and square. If you compare this, square is just like a circle. It's not exactly same, it's just like a circle. If you want to better, you just take a pentagon. It seems like a circle better than the square. You just take the hexagon. It seems like a circle better than the pentagon. You take the octagon. It's better than the heptagon. It seems like a circle. Archimedes thinks circle as a regular polygon, just one with extremely large number of sides. So many sides, in fact, each individual's one side is infinitesimally small, meaning that the circle looks round. Here we take that. You take the circle and two squares. Just draw one square inside the circle and draw another square outside the circle. The inside the square is there. This square, all the edges of this square touching this circle. And outside square, all the faces of the square touching the circle. Archimedes thought, why not measure the problem as square adding up the length, all of its edges, and dividing the number by its diameter. But what is the diameter of the square? Is it length of its diagonal or length of one of its edges? Archimedes, why don't we have both? Here, you just take that inside the square, like the same circle formula, circumference by diameter. We took like that 4L by root 2L is equal to 2.82 something. It's dot dot dot. And you just take the outermost square, outside square, by using the same formula, 4L by L equal to 4. The difference between these values little big using squares. Both are approximately little big than the comparing to the pi value. Square is much like a circle, but replace the square by pentagon, we get better estimate of pi than square. Replace pentagon by hexagon by heptagon by octagon, etc. We get even more accurate estimates by using the same method. Keep increasing more number of faces inside and outside of the circle, your estimate will get more and more accuracy of pi. That's the idea Archimedes follows. Archimedes used 96 sides shapes, which is called as Anacontagai hexagon. Its pronunciation is too hard. Archimedes shows in this way that an estimate of pi between 3.1408 less than pi less than 3.1429 accurately 2 decimal places. Accurately 2 decimal places. This is the Archimedes' final contribution to science because he was killed by Roman soldiers. After that, he was killed by some of the days. After some days, he was killed by Roman soldiers. The final word of Archimedes is a great word. Great mathematician's final word is, "Don't disturb my circles." After that, Newton and Leibniz, very interesting mathematicians. I love these two mathematicians very much. Leibniz and Newton. When Newton and Leibniz developed calculus in the late 17th century, more formulas were discovered that could be used to compute pi. For example, there is a formula for the arctangent function. Arctangent of x equal to x minus x cube by 3 plus x power 5 by 3, 5 by 5 minus x power 7 by 7 plus up to infinite series. If you substitute x equal to 1, and notice that arctangent is pi by 4. You get a formula of pi. And then John Mencken's formula, earlier 18th centuries. Using the arctangent function to calculate pi is not useful because it takes too many terms to get any accuracy. But there are some related formulas that are very useful. The most famous of this is John Mencken's formula, that is pi by 4 equal to 4 arctangent of 1 by 5 minus arctangent of 1 by 239. This formula and similar ones were used to push the accuracy of approximation of pi to over 500 decimal places. It's amazing, 500 decimal places by the earlier 18th century. This was all and calculation. That is a very big thing. There's no computer, no technology is there, but they only use the and calculation. They find 500 decimal places in the 18th century. In the 20th century, there have been two important developments: the invention of electronic computers, the discovery of much more powerful formulas of pi. In 1910, the great Indian mathematician Ramanujam discovered the following formula for pi. It's nothing but 1 by pi equal to 2 root 2 by 9801, summation n equal to 0 to infinite, 4n the whole factorial, 103 plus 26,390 n divided by n factorial the whole power 4, 396 whole power 4n. In 1985, William Gaspar used this formula to calculate the first 17 million digits of pi. Electronic computers since the 20th century. From the mid 20th century onwards, all calculation of pi have been done with the help of the calculators and computers. George Revitzner was the first person who used an electronic computer to calculate pi in 1949 on the ENIAC, a very earlier computer. He computed 2037 decimal places of pi. In the earlier years of the computer, an expansion of pi to 1 lakh decimal places was computed by Maryland mathematician and Daniel Shanks and its teams at the United States Naval Research Laboratory in Washington, D.C. The first 1,265 decimal places of pi were published in 1962. This is the first publication, 1962. Continued. In 1989, the Chudovsky brothers correctly computed pi to over 1 billion decimal places on the supercomputer IBM 3090 using the following variation of Ramanujan infinite series. This is the Ramanujan infinite series. The following Ramanujan infinite series, they calculate that the 1 billion decimal places of the pi value. In 1999, Yashosa Canada and his team at the University of Tokyo correctly calculated over 200 billion decimal places. Itachi 8000 MPP using another variation of Ramanujan's infinite series of pi. In October 2005, they claimed to have calculated it to 1.24 trillion places. That is amazing. In the 21st century, current claimed world records. These are the some in August 2019 Japanese supercomputer, and in December 2019 these records are tabled in the further slide. So I just skip this slide. So next, deriving pi by Buffon needles method. One of the wonderful method to deriving the pi. Buffon needle method is one of the oldest problem in the field of geometrical probability. It was first started in 1777. It involves dropping a needle on a lined sheets of paper and determining the probability of the needle crossing one of the lines on the page. The remarkable result is that the probability is directly related to the value of pi. That is the amazing one. The following page will present an analytic solution of the problem. So before that, I will enter into some experimental Buffon's needle experiment. The setup: you take one white paper and just we drop n needles of length L onto the floor with strip with 2L length. I will take n equal to 314 needles. That means total number of needles I took 314. Next, this is the length of the needle. This is L needle length, and this is the length of the line between this space 2L. If I randomly drop some needles, 340 needles, I took 340 needles. No, randomly I drop the needles. I just pick after I drop the needles. I just pick where the needles will cross the line that intersect these lines. I will pick that needles. Here, this one, and this one, like that. This one and this one, like that. I collect the needles. After that, one interesting fact is that let's count how many needles cross a line. That is 101 out of 340 needles cross the line. Just number of needles by needles across the line 314 by 101 is approximately 3.109. Is nothing but nearer the value of pi. That is amazing one. That's quite interesting to see this experiment. This is the analytical solution for the Buffon's needle method. Let's take the simple case first. In this case, the length of the needle, they generalize the case. The length of the needle is 1 unit and the distance between the lines is also 1 unit. We just take that this length of the needle is 1 unit and the distance between the lines is also 1 unit. There are two variables. The angles at which the needles falls is theta. Needle falls, the angle is theta. And the distance from the center of the needle, the closest line, this is the closest line. This distance is d. The theta can vary from 0 to 180 degree. Theta can vary from 0 to 180 degree and is measured against a line parallel to the lines of the paper. The distance from the center to the closest line can never be more than half the distance between the lines. The graph alongside displays the situation. The shaded portion is found with using the definite integral of 1 by 2 sin theta evaluating from 0 to pi. This results that shaded portion as a value of 1. The value of the entire rectangle, you check the value of the entire rectangle is 1 by 2 pi or pi by 2. So the probability of the it is 1 by pi by 2 or 2 by pi. That is approximately 0.6366197. To calculate pi from the needle drops, simply take the number of drops and multiply it by 2, then divide by the number of 2 into total drops by number of hits equal. The other cases, there are two other possibilities of relationship between the length of the needles and the distance between the lines. Good discussion of this can be found in 1974 by Socrates. The situation in which the distance between the lines is greater than that the lines, the needles is extension of the above expansion, above explanation, and the probability of it is 2L by K pi, where L is the length of the needle and K is the distance between the lines, length of the needle and distance between the lines. The situation in which the needle is longer than the distance between the lines leads to be more complicated results. That is one amazing fact. Then this is the record of historical evolution of approximation of pi. This is the graph I shown here. Next one is, where does this fraction comes from? We all use the formula for area of a circle pi r square. For pi, 22/7 is substitute in the area formula. Where does this fraction comes from? First of all, this is quite interesting. See this diagram. This one radian is an angle suspended by two radii and an arc. This is one radii and this is one radius. Two radii and an arc, all in equal length. All are equal length. Just take this structure. Next, the angle equal to 2 radian. If I increase the angle to 2 radian, then the structure is like this. Then I will move to the angle equal to 3 radian. The image is like this. So it does not cover all the places. Some place is balanced. If the angle equal to 3 radian is removed from the above diagram, from the total angle of pi, radian left over angle is approximately 1/7 radian. The leftover arc length is approximately r/7. I just take that r/7, that 1/7 is the right hand side. This is the space. Now, if leftover angle 1/7 radian is brought on the right hand side, then it look like. If angle is increased by 1/7 radian, then it look like this. If angle is further increased by 1/7 radian, then it look like this. Then up to further increased by 1/7 radian, further increased by 1/7 radian, up to 7 times will get 7 times will get 7/7 is nothing but 1 radian. We'll get 1 radian. After that, I will increased by 1 radian. I'm getting this 14/7. That is nothing but 2 radian. It becomes. If angle is further increased by 1 radian, it becomes 21/7. This is 3 radian is nothing but 21/7. The remaining part already we found, that is nothing but 1/7 radian. If you add this, finally we getting 22/7 is approximately 5 radian. This is the amazing fact that pi is approximately 22/7. Thus, pi is approximately 22/7, 3.142854142. Exactly, if you compare with the pi, exactly 2 decimal places are same. 22/7 is exactly 2 decimal places are same with the comparison of pi. So precisely by definition, pi equal to, we know that circumference by 2 radius, where c is the circumference, r is the radius. And then I want to try to prove pi is irrational. So before that, I will just explain the decimal expansion. This is very important that we understand that why pi is irrational. Decimal expansion. The decimal expansion is divided into 2 types: is terminating one and non-terminating. Terminating means nothing but, if you take any fraction number 1/4 is equal to 0.25. That is an end, and we evaluate this value. 2/5, 0.4. Root 4, there is a 2. Root 16, there is 4. So there is an end for the value. Then the value is called terminating decimal place. That means terminating value. Non-terminating means there is 2 types of non-terminating is there. One is repeating and non-repeating, or recurring and non-recurring. In the non-terminating, recurring means, that means repeating means 1/3 equal to 0.3 bar. That means it goes 1/3 equal to 0.333 up to infinite. 1/11, you take 1/11 is equal to 0.0909 till that it goes to infinite. Does not end, but all the digits are known. We can evaluate the exact value for this type of rational, this type of fractions. But in the non-recurring, that means non-repeating, root 2 equal to 1.412. There is no pattern is repeated here. So this is called non-recurring. This is a type of non-terminating, non-recurring. If take a root 3, 1.73250, here also we are not able to find any pattern that is repeated. Cannot find exact value. All digits are unknown, not exact value. This is the decimal expansion. Short note of decimal expansion. We will go to the rational number because we are trying to prove that pi is a irrational number. For that, first we know about the rational number. But rational number is two types. It's nothing but terminating one and non-terminating recurring. What is the, you take the, we already know in the previous slide we discussed about that terminating and non-terminating and all. We just go to the example. If I take the numbers 5 by 2, 7 by 15, 8 by 15, 9 by 20, 7 by 6, 17 by 6, 11 by 21 for the example numbers. You convert it as a decimal numbers. Here I convert these numbers, these fraction numbers to the decimal form. Now I just find that what form is this. First one is 2.5, that is an n, so it is terminal. 3.4, that is an n, so it is terminal. This is 0.5333 up to infinite, so there is no n, but we know the exact value for this. So it is non-terminating repeating, that is non-terminating recurring type. So next one is terminating, and next one is non-terminating recurring type, and next one is non-terminating recurring type. From these examples we can observe one result. What is that means? Without converting the decimal form, without converting this rational number to the decimal form, we can easily find it is recurring or it is terminating or non-terminating recurring. How? See, quite interesting is this. Just take the q values of all the numbers and find the prime factors of all the numbers. The prime factors of all the numbers is nothing but 2. Here 5. Here 3 into 2. Product of the prime factors. Here 2 square into 5. Here 2 into 3. Here 3 into 7. You just observe one thing. What is that means? For terminating process, only 2 and 5 will exist. So we just conclude one result. 2 or 5 are both in the q value. The q value is 2. The prime factor of q value is 2 or 5 or both. Then we conclude that it is a terminal. If the q value, factor of the q value is other than 2 or 5, including 2 and 5, and other than 2 or 5, then we conclude that non-terminating recurring. This is the general equation, general conclusion for the q value. If q equal to 2 power m into 5 power n, then we conclude that it is a terminating. The q equal to 2 power m into 5 power n into k, for m and n are the integers, then k be the prime factors other than 2 or 5, then we conclude that it is a non-terminating recurring. By using this formulas, we can easily find that rational number is terminating type or non-terminating recurring type without converting the decimal form. This is the quite interesting result we discussed before. Next we will move to the irrational number. That rational number covers 3 places, that is nothing but terminating and non-terminating recurring. Remaining part is non-terminating, non-recurring decimal numbers that are called irrational numbers. If you take root 2 is an example, there is no any repeating pattern. We are not able to find the repeating pattern that follows up to infinite. Up to infinite it is different only. So it is a irrational number. By following that, we conclude that pi is also a irrational number, because in the pi also there is no pattern follows up to infinite. So we conclude that pi is a irrational number. So properties of pi. Next we will go to the properties of pi. I love this equation. One of the famous pi equation connects the first to most important numbers in mathematics. That is 0, 1. It will include 0, 1, e, pi, and I. I think all the numbers included in this equation. This is one of the famous and beautiful equations. The property. In this equation, pi is one of the parts. That is amazing fact. And the digits of pi. Pi is an infinite decimal. Pi has infinitely many number to the right of the decimal point. If you write pi down in the decimal form, the number to the right of the 0 never repeating in the pattern. Although many mathematicians have tried to find it, no repeating pattern for pi has been discovered. In fact, 1768, John Lambert proved that there cannot be any such repeating pattern. As a number that cannot be written as a repeating decimal or a finite decimal, you can never get to the end of it. Pi is irrational. Pi is irrational. It cannot be written as a fraction, the ratio of two integers. And then pi and the area of the circle. The distance around a circle is called the circumference. We know that the distance across a circle through its center is called the diameter. The diameter of a circle is twice as long as the radius, is nothing but equal to r. We already know that. We use the Greek letter pi to represent the ratio of the circumference of a circle and the circumference of the circle to the diameter. For simplicity, we use pi equal to 3.14. Sometimes pi is nothing but 22/7. The final formula for the circumference of circle is nothing but 2 pi r. The area of a circle is pi r square. And then pi in real life. Pi is used in many areas. If you're finding the measurement of circles, cylinders, or shapes such as circumference 1-dimensional, area 2-dimensional, and volume 3-dimensional, student can look for real life application of knowing measurements of objects in these shapes. We'll move, for example, if you get some, I will tell some example. For example, if a student would decide to build a robot, he might want to be able to program the robot to move a certain distance. If the robot is made with wheels that have a 3 inches diameter, how far would the robot move with each complete rotation of the wheels? This would be a circumference problem, as the robot would move the length of the circumference with each rotation of its wheel, in this case 5 pi, or approximately 15.7 inches. This is the real life problem we using the pi. Facts of pi. Some of the interesting facts. Pi is the most recognized mathematical constant in the world. Scholars often consider pi the most important in all the numbers in all the mathematics. The symbol for pi has been used regularly in its mathematical sense only for the past of 250 years. In the Greek alphabet, pi was the 16th letter. Pivas means this is the 16th letter. The better way to approximate pi. We know that pi is nothing but 3.145926 up to infinite. But in the better approximation is first is 22/7, first 2 decimal places. It will a better approximation of first 2 decimal places. And this number, quite interesting number, 355 and 133, 355 by 133, quite interesting. For first 6 decimal places is approximately first 6 decimal places are equal when comparing to the pi. And this number is first 9 approximate places of pi. It's quite the better ways to approximate of pi. These are the numbers. That 3551113, that number is a Ramanujan number. Ramanujan approximately construct with the approach of 355 by 113 by geometry. The Chinese mathematician also work in this number. The same. This is the data I already told you. No, this is the data that a list of the programmers and finding the digits of pi. Data on programmer, time, and digits of pi. These are the list. One thing I want to say in this time, நிறைய பேர் வந்து யோசிக்கலாம், என்ன யோசிக்கலாம்னா, இந்த பையோடைய வேல்யூ இத்தனை டிஜிட்ஸ் வந்து எதுக்காக கண்டுபிடிக்கணும்? why they are finding these values? what is the use purpose? first of all, இதை நான் திங்க் பண்ணும்போது என் மைண்ட்ல பட்டது, இப்போ ஒரு எக்ஸாம்பிளுக்கு ஸ்விம் பண்றோம், எல்லாருக்கும் ஸ்விம்மிங் தெரியும். எல்லாருமே வந்து பாத்தீங்கன்னா ஸ்விம்மிங் தெரிஞ்ச எல்லாருமே ஓஷன்ல வந்து ஸ்விம் பண்றது இல்லை. சம் ஆஃப் த பர்சன் ஸ்விம் இன் ரிவர், சில பர்சன்ஸ் வந்து லேக்ல, சில பர்சன்ஸ் வந்து ஸ்விம்மிங் பூல்ல ஸ்விம் பண்ணுவாங்க. அப்போ வெரி டிஃப்ரெண்டா, வெரி லெஸ் பீப்புள் ஒன்லி ஸ்விம் இன் த ஓஷன். ஸோ இவங்களெல்லாம் எனக்கு இந்த மாதிரி பர்சன்ஸ்லாம் தே ஆர் ஸ்விம் இன் த ஓஷன்ஸ், அது மாதிரி தான் பார்க்க தோணுது. தே ஆர் டிஃப்ரெண்ட் ஃப்ரம் அதர்ஸ். ஸோ திஸ் இஸ் த pi value of up to 100k decimal places. First page of pi value 100k decimal places. This is the first page, and this is second page of pi value of first 100k decimal places. It does not end. Till August 2021, Swiss researchers calculate pi to new record of 62.8 trillion digits. ஈவன் இந்த பையோடைய வேல்யூவை கால்குலேட் பண்றது மூலியமா இந்த சூப்பர் கம்ப்யூட்டர் ஸ்பீடை கூட கணிக்கிறாங்க. இந்த பையோடைய வேல்யூ எவ்வளோ ஃபாஸ்ட்டாக கால்குலேட் பண்ணுதுன்றது பேஸ் பண்ணி சூப்பர் கம்ப்யூட்டருடைய ஸ்பீடை கூட என்ன பண்ணுறாங்கன்னா கால்குலேட் பண்ணுறாங்க. தட் இஸ் இன்ட்ரெஸ்டிங் ஃபேக்ட் அபவுட் த பை. ஆகஸ்ட் 2020 இவ்வளோ டிஜிட்ஸ் வந்து ஃபைண்ட் அவுட் பண்ணியிருக்காங்க, 62.8 ட்ரில்லியன் டிஜிட்ஸ். அண்ட் ஃப்ரீக்வன்சி அனலைஸ் ஆஃப் த ஃபர்ஸ்ட் 200 பில்லியன் டிஜிட்ஸ் ஆஃப் பை. 0 எத்தனை டைம்ஸ் ரிப்பீட் ஆயிருக்கு, 1 எத்தனை டைம் ரிப்பீட் ஆயிருக்கு, ஃபர்ஸ்ட் 200 பில்லியன் டிஜிட்ஸ்ல இத்தனை டைம்ஸ் வந்து ரிப்பீட் ஆயிருக்கு. 1, 2, 3, 4 and 5, 6, 7, 8, 9. These numbers I think first 200 billion digitsல 8 will occupy the first place. More number of repetition. 8 வந்து இத்தனை டைம்ஸ் ரிப்பீட் ஆயிருக்கு. I think so. I think yeah. Yes. 8 will occupy the first place. It's a quite interesting one. The Pi Day. Pi Day is the unofficial holiday. The mathematics constant Pi. Pi Day is observed on March 14. Since 3, 1 and 4 are there, 3 most significant digits of pi in the decimal form. In 2009, the United States House of Representatives supported the designation of Pi Day. Pi approximation. Today is the Pi Approximation Day. Pi Approximation is observed on July 22 or 22/7 in date and month format. Since the fraction 22/7 is the common approximation of pi. This is a quite interesting website page, Pi search page. If you go to this Pi search page, if you enter your any number, if you enter your phone number or password of date of birth, it will shows that I enter my date of birth here. The string by date of birth is converted as a string. The string occurs at position. In this position, my string is occurs. How many time means only one time. This string is occurs one time in first 2000k decimal places, 200 million places. என்னுடைய ஸ்ட்ரிங் வந்து ஒன் டைம் வந்து அக்கர் ஆயிருக்கு. ஸோ நீங்க இல்லை பாஸ்வேர்டு எது போட்டாலும் சரி, இந்த நம்பர்ஸ் வந்து நம்மளுக்கு வந்து அந்த ஸ்ட்ரிங் மாறாம அப்படியே வந்து அக்கர் ஆகுது நம்ம பார்க்கலாம். இந்த வெப்சைட் பேஜ்ல பை சர்ச் வெப்சைட் பேஜ்ல போய் பார்த்தீங்கன்னா தெரியும். Finally, in mathematics, an opinion without pi is just an onion. It's just a fun factor. I wishing you happy Pi Approximation Day. I hope that this session will useful for everyone attending this seminar. So thank you for all present here. If any questions? Thank you, sir.
மிக்க நன்றி ஐயா. மிகவும் மகிழ்ச்சியாக இருக்கிறது எங்களுக்கு. வெகு சிறப்பாக நடைபெற்று கொண்டிருக்கின்ற இந்த பை தோராய தின நிகழ்வில் மிகவும் அழகாகவும் சிறப்பாகவும் நீங்கள் உரையாற்றி இருக்கிறீர்கள். உங்களது உரையின் மூலம் ஏராளமான தகவல்களை நாங்கள் தெரிந்து கொண்டதோடு உலக அளவில் புகழ்பெற்று விளங்குகின்ற கணித மேதைகளின் ஆராய்ச்சிகளிலே பை எவ்வாறெல்லாம் இணைந்திருந்தது என்பது பற்றியும், இந்த பையினுடைய மதிப்பு காலந்தோறும் எப்படிப்பட்ட மாற்றங்களை பெற்றிருந்தது என்பது பற்றியும் பல தகவல்களை நீங்கள் கொடுத்திருக்கிறீர்கள். மீண்டும் எங்களது பை கணித மன்றத்தின் சார்பாக நெஞ்சார்ந்த நன்றியை நாங்கள் தெரிவித்துக் கொள்கிறோம். இப்பொழுது இந்த நிகழ்விலே கலந்து கொண்டிருக்கின்ற அனைத்து அன்பு உள்ளங்களுக்கும் ஏராளமான வினாக்கள் வந்திருக்கலாம். உங்களுடைய வினாக்களை இப்பொழுது பதிவு செய்யும் நேரம். உங்களது வினாக்களுக்கு சிறப்பு விருந்தினர் அவர்கள் பதில் கூறுவதற்கு தயாராக இருக்கிறார்கள். வினாக்களை நீங்கள் தொடுக்கலாம். பரவாயில்லை. கதிரவன் ஒளியிலே பனித்துளி கரைந்து போவது போல சந்தேகங்களே இல்லாத வகையில் வெகு சிறப்பாக நமது சிறப்பு விருந்தினர் உரையாற்றியிருக்கிறார் என்பது வெட்ட வெளிச்சமாக தெரிந்துவிட்டது. நிகழ்வில் அடுத்தபடியாக இந்த சிறந்த பை தோராய தின நிகழ்வில் நன்றி உரை கூறுவதற்காக அன்பிற்குரிய ஆசிரியர் விஜயகுமார் ஐயா அவர்களை அன்போடு அழைக்கின்றோம்.
Good evening to all. I feel honored to propose this word of thanks on behalf of Pi Mathematics Association. I use this opportunity to thank our founder, Professor Dr. R. Sivaraman, for initiating this wonderful lecture. And I thank Mr. Kalyan Kumar, who joined from Kuala Lumpur, Malaysia, for giving an introduction about the speaker. He is one of the active member in our association. And I thank Professor Chellapillai sir for this wonderful comparing in Tamil. He is one of our Pi Mathematics Association family. Even though he is a Tamil professor, but is very much interested in mathematics. He always ready to help us in our all programs without expect anything. Now I thank the speaker, D. Anand, teaching fellow Department of Applied Science and Mathematics, Anna University, MIT campus. The way you share the information about Pi is very much clear and understandable. I am sure it will be very much useful to all. Definitely it will be very useful to all the participants, because the way you share the information is very much clear. So I thank the speaker, D. Anand, once again. And not but not least, I have to thank all the participants on behalf of Pi Mathematics Association. Because of you only this program become a successful one. So I thank everyone for joining this lecture. Thank you again on behalf of Pi Mathematics Association to one and all. Thank you.
நன்றி ஐயா.
Thank you all. Thank you.
சிறந்த இந்த நன்றி உரைக்கு மீண்டும் நன்றியை தெரிவித்துக் கொண்டு வெகு சிறப்பாக இந்த நிகழ்வு இத்துடன் நிறைவடைகிறது. மீண்டும் விரைவில் எங்களது பை கணித மன்றத்தினுடைய அடுத்த நிகழ்வில் உங்கள் அனைவரையும் சந்திக்கலாம். மிக்க நன்றி. அனைவருக்கும் வணக்கம்.